Okay, kids, time for 5.2 Graphs of Logarithms. So what we're going to do here is we're going to look at basically the shape of log graphs, some other important features, and how to transform them. So not a really hard lesson here because we're just applying something we already know to a new idea. So recall that a logarithmic graph, it is the inverse of an exponential. So from the last unit, we know that the graph y equals c to the power of x. This could be whatever, it could be b to the x or c to the x. This has a domain, x is all real numbers, and a range y is greater than 0, because all exponential graphs tended to do this kind of thing here. The logarithmic graph then, because it's the inverse, we swap x and y, so the properties basically just do this. So what we can say for logarithmic graphs, the domain is x is bigger than 0. And y is all real numbers, because you can get any value of log you want. The intercept, y is equal to 1, and it becomes x is equal to 1. So right here you have 0, 1 on the exponential, and on a log you have 1, 0. And then same thing with the asymptotes. We used to have a, let's stick with the right colors. We used to have a horizontal asymptote at y is equal to 0 for the exponential graph. Oh, that's a total lie. That's a total lie. Sorry. Why did I just draw like that? We have a horizontal asymptote like this, and then we have a vertical asymptote for the log graph going like that. And then, of course, the key points 0, 1, and 1, c. So the reason why I'm writing 1, c is it depends on what the base is, right? If the value of the base is 2, then when x is 1, y will be 2, and same thing over here. So 1, 0, and c, 1. And of course, everything's going to change when transformations are applied. You don't really have to memorize this, but I thought it would be nice just to kind of show in a chart how everything changes. So what would be really handy here is if we just took a second, we drew some log graphs with different bases, because that's what's going to ultimately change the shape of it, as well as transformations later on. And we're actually going to see that changing the base from like a 2 to a 5 or 10 is kind of like a transformation, but it's just a little of a non-standard one. So right now, let's just have a little look. If you have the graph log base 2 of x, let's do this one in red, and then I'll do the other ones in different colors. So x and then y equals log base 2 of x. And then we'll go maybe blue for this one. We'll go x. Y equals log base 5, and so on. And this is not a really hard thing, but I really wanted to just show it at least once, how you would graph these log functions here. Okay, so this is x, and y equals log base 10 of x. So the only thing we're going to have to think about here is what values of x are you going to pick? So what we just said is that the domain for all of them, and in fact, I could just go ahead and say this right now. The domain for all of them, x is greater than 0. And this goes for all log graphs. Okay, so regardless of the base, it's always x is bigger than 0. So we're not going to put 0 in our table of values, but we're going to start with 1. So what is log base 2 of 1? So if you're still kind of getting used to this, remember what we're doing is we're saying 2 to the power of what gives me 1. And 2 to the power of 0 would give me 1. So log base 2 of 1 would be equal to 0. The next value of x I'm going to pick, which is a simple one, I'm going to pick 2, because 2 to the power of 1 would give me 2. So remember, log is the exponent to which you must raise the base to get the number that you're logging. The next one that I would do, I would not do 3 because I don't know what power you'd have to raise 2 to get 3, but I would consider 4, because when we're going log base 2 of 4, then I can say, well, that's got to be 2 squared. And if you're starting to get the hang of it, that's great. And then the next one's going to be 8, and we'll have 3. And you'll notice there's a relationship here, right? 2 to the power of 1 is 2, 2 to the power of 2 is 4, and so on. And once you kind of get that idea, you can just go through and rip through all the other ones. So this one will be 1. I'm not going to put 2 down here, but it's log base 5, so I'm going to put a 5. And the next one would be 25, and so on. Okay, and then this could be 0, 1, 2, 125 would be 3. You might notice that that's not going to fit very well on my graph, and you're absolutely right. Logarithmic graphs can be a little tricky sometimes, and I'm just going to do this other one while I'm sort of mumbling stuff here. Logarithmic graphs are sometimes used to show humongous things where the scale is not like 1, 2, 3, but it's actually like 1, 10, 100, 1,000. You might have seen some stuff like that as well. Okay, so graphing all of this here, we said the domain x is greater than 0, the range, same thing, y is all real numbers, and again, it's for all log graphs, so we're not going to have to worry about this too darn much, okay? And the intercepts are pretty simple. They all have the same x-intercept, no matter what, okay? So all we're going to do is we're going to just sketch this here. I am going to just go 1, 2, 3, 4, 5, 6, 7, and I'm going to go 1, 2, 3, 4, 5. I'm not going to make a number everywhere, 10, and 1, 2, 3, 4, 5, 15, and so on. Okay, so this will wind up being 1, 0. So the red data is going to go in here. 2, 1 will go right up here, and then we'll go 4, 2, and then 8, 3, and so on. And we could even get smaller if we wanted. We could have values of x that are less than 1, but you know what? For now, I'm just not that worried about it. Okay, I know they're going to asymptote down. I know this one's going to go like this, and there's going to wind up being some more values later on, but I'm not that fussed about getting it perfect. The blue one. So what we can see with the blue one's also going to go through this point. Maybe I'll just put an X or a different symbol there. And then we're going to have 5, 1. And then we're going to have 25, 2. So already we're way off here. So this graph is going to do this sort of thing. It's going to go like, and it's going to shoot off here. That sound effect, by the way, that's really important. That'll be on the test. Make sure you get okay. And it's going to actually get a little closer to the y-axis there, a little sooner than the other one. And then this one is going to go, again, green. I don't know, I can stick a triangle there, 10, 1. I'm not even going to try and put 100. But what we can see here is we can see that when the base gets bigger, the graph gets a little scrunched. Now, does it get scrunched horizontally or vertically? What we can see here is because this point never changed, so 1, 0 is invariant, would be the fancy way of saying it. What we can conclude is there's no horizontal stretch. Just about to say shift. There's no horizontal stretch. What's happening is all the points are getting moved up and down. So changing the base is equal to a vertical stretch. If it was a horizontal stretch, that key point 1, 0 would be moving left and right, but it's not. It's moving up and down, and because it's already on 0, multiplying it by some factor is not going to be moving it. So changing base is what gives us a vertical stretch. Okay, so that's not the only way we can do it, but that is something worth knowing, and later on we'll prove exactly why that is when we get to the change of base rule. All right, so the general transformations for the logarithmic function. Now this explains why we've been using that awkward C. I kind of like B for base, but C is there because if we want to use A, B, H, and K the way we have been so far, well, we need log base C, so we're not sharing the same thing. Although, to be honest, a lot of times textbooks will use log base B, and I don't blame them. I kind of like that myself. But anyway, okay, so A is the vertical stretch, B is the horizontal stretch, blah, blah, you get all this sort of stuff. And of course, as we just discovered, modifying the base C also affects the vertical stretch. It's not an obvious way, and we'll cover that later. Not much else to say about that. Okay, so most of what you need to be able to do is draw the log graphs and apply transformations. So when we have log base 3 here, I think what would be useful is before we do anything, let's just sketch that. So log base 3 is going to have some key points. Key points will be x and y equals log base 3 of x. So again, 0 is never going to work, but 1 will work, and 1 will get us to 0. because we're log base 3, we'd want to have 3, and we'd want to have powers of 3, and so on. So what we could do here, and we're assuming everything's just one grid. Okay, so there's 3, 1, and then I guess this goes off grid, but like 9, 2 would be there. And what we would have is we'd have this sort of situation. Okay, so that would be my graph. That's like the parent function. It's a little tricky here because there is no base of logs that is always like standard. I know 10 sort of is, but when we're talking about parent functions, we've got to think the base can change. Okay, so that's like my parent function, y is equal to log base 3 of x. And then simply we just have to look at this and go, okay, what does adding 9 to the argument do? And we've seen this enough that we should know that goes 9 to the left, and then this goes 2 up because it's added to the outside of the log. Remember, the function is log, so this whole thing would read like f of x plus 9, and then this little bit at the end is like my plus 2. Okay, so determine the equation of all asymptotes, find the intercepts, state the domain and range. Okay, so let's just draw the transformed function. So I'm going to draw y is equal to log base 3 of x plus 9 plus 2 in blue. So that means everything goes over 3 spaces. If we want to do mapping notation, we could even do that as well. The mapping notation would be x comma y. That's a funny looking y. And it would go over to x minus 9, and we'd have y plus 2. So we could take some key points like 1, 0. We could move it over to negative 8, 2. We could take some other points and do that if you like. That would be negative 6, and that would be 3, and so on. So what we'd have is we'd have a point at negative 8. Okay, so I should have made this graph a little bit bigger. So negative 8, 2 is about right there. And then we'll have negative 6, 3, which is right about there. Okay, we'll also have the vertical asymptote moves from x equals 0 to x equals negative 9. So over here, I guess something like this. There's my vertical asymptote at x equals negative 9, and we'd have this graph kind of doing this sort of deal. Now, there's a couple points, but we'd like to get the intercepts, and how we're going to get the intercepts exactly is the same way we're always going to do it. This is going to require a little bit of math, and well, that's good because we can do that. Okay, so x-intercept, we're going to set y is equal to 0, and we're going to solve. So if we have y equals log base 3 x plus 9 plus 2, we're going to set that equal to 0. We're going to have to solve that. So I'm going to erase this y here, and I'm going to put in a 0. So the way we're going to solve for x is very simple. We're going to move 2 to the other side by subtracting it. And now we have, we've got a bit of a situation here. We've got to turn this into something that doesn't have a log. So I'm going to convert this into exponential form. So what we're going to do is we're going to say, okay, so what is this as an exponent? Now it's log base 3, so the 3 goes as the base, and remember log equals the exponent, so it's equal to negative 2, so this is going to be 3 to the negative 2, and then the x plus 9 is what's left over. Okay, so we have this, and now we can actually solve. We'll go x equals, now 3 to the power of negative 2 is 1 over 9. So we'll go 1 over 9, and then we'll be subtracting 9 over like that. And I guess with a common denominator, that's what, 81? Whoopsie doodle. That's 1 over 9 minus 81 over 9, which is negative 80 over 9. Which is, yeah, that's what, about 0.8, it's probably 8.88 repeating would be my guess. Anyway, it's a tiny bit less than 9, or I guess greater than negative 9. So what we can see here, that point right there, does that look like that's about correct? That will be negative 80 over 9, comma 0. That actually looks reasonable. And I know my asymptote is at negative 9, so a point that's just a little bit bigger than that makes sense. To get the y-intercept, similar process here. I guess I'll fit it in right here. The y-intercept will set x is equal to 0, and it's a similar process here. I think this will probably be a little bit easier to get. Okay, so whoopsie, that's supposed to be y. So what we're going to have here is we're going to say y is equal to log base 3 of 9 plus 2. What is log base 3 of 9? It turns out that is equal to 2. So my y-intercept should be 4. So what I have here on my graph, if I look at this, holy smokes, okay, well, I'm a lucky man today. Okay, I drew that at 0, 4, and that's exactly where it should be. So I guess I got the curve just right. Okay, so let me just highlight those, and then we'll move on to the next one. Did I do everything? I think I did. Oh, domain and range. We better do that too. Okay. I always forget about domain and range. Okay, domain is really easy. X is greater than -9. You should say X belongs to all the real numbers as well, right? Because that means it's decimals and everything. Y just belongs to all the real numbers. Okay. Okay, pretty simple, but worth doing. Okay, number 2, or B. You may consider trying this yourself. Okay, so if you have given it a shot, or even if you have not, let's have a look at this. So we've got a log 2, which is basically like, we're going to have, let's see, so y equals log base 2 of x. So my important points will have 1, 2, 4, and so on. Do this one quickly because we did something like this earlier. So we'll have 1, 0, we'll have 2, 1, we'll have 4, 2. So our parent function is going to look something like that. Okay, and then it's going to go down to infinity. So that's y is equal to log base 2 of x. Now what we've got here is we've got a little bit of a situation. I'm going to rewrite this as, maybe I'll just switch colors because I'm going to use blue for my transformed one. Y is equal to negative log base 2. We're going to have to take a 2 out of here. Okay, so now what we've got is we've got a bunch of things. We've got a vertical reflection. We've got a horizontal compression by a half. And then we've got 2 to the right. Okay, so for this one, I'm definitely going to want to use mapping notation. So xy is going over, if we're having a horizontal compression by half, we're going to have 1/2 x, and we're moving 2 to the right, so we're going to add 2 to that. Vertical reflection is just going to be negative y. So some key points here, we've got 1, 0, we've got 2, 1, we've got 4, 2, and we can even include the vertical asymptote x is equal to 0. So what's going to happen to all of this? Asymptotes can go in mapping notation as well. I don't know if that's technically correct, but I like to do it. Okay, so in this case, we've got 1/2 x plus 2. So that's 1/2 of 1 plus 2. That's 5 over 2. And then we've got comma negative y. Okay, well, -0, whatever. 1/2 x, so that's 1/2 of 2. I believe that's 3. And this will be -1. And let's see, 2 plus 2 is 4. And that should be -2. And I think I got that good. So we go plot the points. So 5 over 2, 0. So that's like 2.5. So that's going to go right there. We're assuming every grid line is 1. 3, -1 is right here. And then 4, -2 is right here. Okay, that's an interesting thing. So I think what's happening is my graph, oh, let's actually do the vertical asymptote just to be sure. So we go 1/2 times 0 plus 2. That's going to be x is equal to 2. Okay, so I better draw that in because that's going to really help me. Okay, yeah, now that's pretty obvious what's going on. So I've got this graph, it's going here, and it's going to swoosh out that way, and it's going to swoosh sort of up that way. So y equals negative log base 2 of 2x minus 4. Does that look about right? Do we have a vertical reflection? Yeah. Do we have a horizontal compression? It looks a little scrunched and it moves to the right. I think that's pretty good. I guess I'll just do the domain and range right now before I forget. So the domain is x is everything bigger than 2, and the range is y is all real numbers, and we should put x is all real numbers as well. Okay, so let's get the x and y intercept. So we'll go the x-intercept. So we set y is equal to 0, so we're going to have 0 equals negative, let me just remember what that is, negative log base 2 of 2x minus 4. And seriously, if you have not started doing something on your own, this is a really good place to start. Pause the video and give it a shot. So I'm just kind of doing x and y side by side. So the x-intercept will do this. Okay, so this is interesting. The x-intercept here, we set y is equal to 0. So how are we going to solve this thing? Now, we've got to turn this into exponential form. So we've got 2 to the power of 0. And then we've got a negative sign over here as well. So what I'm going to do is, I'm not loving that negative sign. I'm actually going to divide both sides by -1 to get rid of it. So this is something you can actually do, and we're going to learn how you can deal with these negative signs and stuff out front. But I'm going to divide both sides by -1. There's nothing wrong with that. They're gone, and well, this does nothing. So I'd much rather solve this equation. Log base 2 of 2x minus 4. Okay, so now once we've done that, we should be able to say 2 to the power of 0. This is an exponential form. 2 to the power of 0 is equal to 2x minus 4, and that means that is 1 is equal to 2x minus 4. So we'll move the 4 over to get 5, and we'll get 5 over 2 is x. Now, if you're sitting there going, well, didn't we already know that? Yeah, we did. And I didn't even realize that until I just started doing all that work. But hey, there we go. So I'd like to point out that we did already actually know it, but this is how you can solve for it. So I'm going to call that a teaching win, showing you 2 different ways of doing something. I'm totally not wasting my time. Okay, so y is equal to, okay, you know, I'm going to do something very similar here. No, I'm not going to do something similar. I lied. Okay, so this is log base 2, 2 to the times 0 minus 4. So this is log base 2 of that. Okay, so what this is saying here is we now need to evaluate this guy. I don't like that -4 so much. So to what exponent do I have to raise 2 to get -4? 2 to the power of what equals -4? I don't think that works. Oh, we're trying to take the logarithm of a negative number. There's no solution. This isn't possible. Does that make sense? If we go up to our graph, oh, look at that. There's an asymptote here. Our blue graph never crosses over the y-axis, so there is no solution. And that would explain why I'm trying to take the log of a negative number. Yeah, okay, that doesn't work. So anyway, no solution. There's no intercept. Therefore, no y-intercept. Cool beans. All right. Last couple of questions. Determine the equation of the following logarithmic functions which have been stretched. This part's here because they could have been translated, but that actually gets a little bit too tricky. So you're told that they've been stretched. So has this been a horizontal or a vertical stretch? We don't actually know right away. So what we're doing is we're looking for this very important clue, this point here. So this tells us, that there's a horizontal compression. And the reason is it would normally be at 1, 0, but it's at 0.25, 0. So what we can deduce from this is a factor of 4, or f of 4x. That's what we can determine. Okay, so this is 1/4 the distance it should be normally. So this is a horizontal compression by 1/4. So whatever our function is, we're going to have 4x in the argument. So this is going to give us, what we know so far, is we're going to say y equals log of 4x. Now the challenge here is we don't know what the base is. So what's the base? And the way we're going to do that is we're going to think about, okay, if this was just y is equal to log without log base c of x, we're going to look at this and we're going to go, okay, well, what if all these points weren't horizontally compressed? So if these points weren't horizontally compressed, they'd all shift out to 4, 1. This one would shift over to 1, 0, and this one would shift all the way over to 16, 2. So what we can do here, I'm just maybe going to sketch something here. I'm going to get rid of this stuff here. The non-stretched parent function would look something like this, or the non-compressed, I guess. Okay, so this would just sort of be, that's a terrible curve, but you get the idea. Okay, this would be y is equal to log base c of x, and this would be y is equal to log base c of 4x. So we just need a way of figuring out base c, and what you can do here is there's not really an amazing mathematical way to do this, although you could do it forcing it with algebra, but what we should be able to do is we can see that my points are 1, 0, 4, 1, 16, 2, and what we should be able to conclude is that therefore the base is a log base 4. Okay, we can see these are all powers of 4, and let me just write a little statement down here. Since points have x coordinates that are powers of 4, the base must be 4. Oops, must be 4. If you don't like that, you can always go ahead and you can say, okay, well, I could sub in one of these bases, one of these points, and I could say, well, when y is 1, x is 4, so then putting this into exponential form, this would be c to the power of 1 equals 4, therefore c is equal to 4. You could do it that way too. So this is an alternative method using algebra. This is the algebra method, but I'm just kind of a big fan of just sort of looking at it. Okay, so what's our final equation? So therefore, putting it all together, y is equal to log base 4 of 4x. I'll put a box around that. Okay, if we look at this one, so has this been horizontally or vertically stretched? And we can see this point right here. So that's at 1, 0. Therefore, there's no horizontal stretch because that would have moved. That's the key point that's on all log graphs. And if it's there, that means there's no horizontal stretch. Now, is there a vertical stretch? What we can see here is we can see the distance here has a vertical distance of 2 and 4. Whereas in my last graph, there's a vertical distance of 1 and 2. So what we can deduce from this is we can say there's a vertical stretch by a factor of 2. So therefore, we know that y equals 2 log base c of x. If we want to do this in like function notation, it would be 2f of x. Okay, so what we have here is we've got an issue where we want to figure out the log base c. Now, those of you who are saying, I really like the algebra, let's use the algebra method. So using the point, let's see, we can use 3, 2 or 9, 4, it doesn't matter. But using the point 3, 2, we can put in 2 for y. We can say 3 belongs over here. And if we solve this for c, well, we divide both sides by 2. So we could grab, let's see here, so we could go divide by 2 on both sides, nothing wrong with that. Cancel, cancel. Don't you dare cancel the 3 in with the log. That's not something you can do. Cancel those out, you'll be left with a 1. And what you've got now is you've got 1 equals log base c of 3. And again, this would be c to the power of 1 equals 3. Therefore, c is base 3. So putting this all together, we could say finally y equals, what the heck? Y equals 2 log base 3 of x. Similarly, we could have looked at this and said, there's 3, there's 9. Those are all powers of 3. We could have set the base was 3 just based on the powers. Based on. Okay, anyway, that's enough bad jokes for me, and I'll see you later.